Welcome to the deep dive. You sent us a really interesting stack of material.
Yeah, quite a mix.
And our mission today is, well, to cut through it all, really, and pull out the key insights into how science works, what it is, basically.
The nature and the methods.
Exactly. So think of this as your personal tour. We'll touch on why science even exists, how scientists do their thing, some of those big philosophical arguments.
And even the stuff science maybe can't answer.
Right. We're not writing a textbook here, promise. We want those aha moments, that clearer picture of what science is all about. Okay, let's get into it.
Sounds good. So maybe start with the why. Why do we even do science?
Good question.
Well, at its heart, and you see hints of this in the sources, science is really driven by this desire to understand the world around us. Ayer asks about the nature of a material thing.
That basic curiosity, what is this stuff?
Precisely. That drive to figure out what things are made of, how they work. It's fundamental. And it's not just random guessing. There's this underlying assumption, right?
An assumption that
the universe isn't total chaos, that there are principles, patterns, things we can actually figure out if we look systematically.
Okay, so curiosity plus a belief that answers are actually findable. Has it always been like that, though? This focus on, well, systematic looking?
Not exactly. I mean, if you look back historically, explanations often came from very different places.
Like religion, or just pure argument.
Yeah, reliance on religious dogma, philosophical reasoning that wasn't necessarily grounded in observation. You see echoes of this contrast in things like Mill discussing religious liberty, or even Plato's dialogues comparing different ways of knowing.
So the shift towards evidence we can actually check, testable ideas, that was a pretty big deal.
A huge development. It really sets the stage for modern science.
Okay, so that's the aim, the sort of historical context. But then there's this other big question. How do we tell real science apart from things that just, look scientific? That line feels fuzzy sometimes.
Oh, it absolutely can be. That's the demarcation problem, as philosophers call it. It's crucial sorting out rigorous science from pseudoscience or even just non-science.
So what's the key difference then?
A lot of it comes down to validation. How do you know if something is right? If you look at, say, Confucian ethics or Taylor on authenticity or Nietzsche's critiques, they offer deep insights.
Sure, definitely thought-provoking.
But their methods, the way they arrive at conclusions and how you judge their truth, it's just different from science. Science generally demands empirical evidence.
Stuff you can see, measure.
Exactly. And hypotheses you can actually test and, crucially, potentially prove wrong. Falsifiability. Plus, a willingness to change your mind if the data doesn't fit. That's key.
Okay, so testable evidence, the risk of being wrong. That's central to the scientific approach. So when scientists actually, get down to work, what are their main tools, the practical stuff?
Well, the absolute bedrock methods are observation, experimentation, and measurement. That's how scientists collect evidence about the physical world.
Watching, poking, and counting, basically.
Yeah, in a way. Observation is careful, systematic watching. Experimentation means actively changing something to see the effect. And measurement. Well, that lets us put numbers on things, quantify observations, makes them precise, allows for math.
And they all work together.
Definitely. They provide the objective data you need to build on.
Right. But then you have all this data. How do you make sense of it? How do you go from seeing, say, apples falling to a theory of gravity?
Okay, that's where reasoning comes in. Two main modes. Induction and deduction.
Induction and deduction.
Right. Induction is kind of like playing detective. You see lots of specific instances, lots of apples falling, and you infer a general rule or pattern, like maybe all objects with mass attract each other.
Okay, specific to general.
And deduction is the reverse. You start with the general theory, Newton's law of gravitation, say, and you deduce specific testable predictions, like if this theory is right, then this satellite should orbit at this speed.
General theory to specific prediction. Got it. Both sound essential.
They absolutely are, constantly cycling between observing, generalizing, predicting, testing.
I've also heard scientists talk about unification and reduction. What are those about? Feels like big picture goals.
They are, definitely. Unification is this really powerful drive to find overarching laws or theories that can explain lots of different looking phenomena under one roof.
Like physics explaining chemistry, maybe? Or parts of biology?
Sort of, yeah. Or think about how the laws of electromagnetism explain electricity, magnetism, and light all as aspects of the same fundamental force. That's unification.
Reduction.
Reduction is the strategy of understanding complex things by breaking them down into their simpler parts. So understand a whole organism by understanding its cells, understand the cell by understanding its molecules, and so on.
Makes sense. Break it down to understand the whole.
It's incredibly successful in many areas, though it's an interesting question whether it always works perfectly, especially when you get to really complex systems like, say, human society. Some sources you sent touch on more interdisciplinary approaches there.
Right, that makes sense. Okay, this paints a clearer picture of the how, but it also kind of opens up deeper questions, doesn't it, about what scientific knowledge really is.
Absolutely, and that's where the philosophy of science comes in. It really grapples with these foundational issues.
Like what, for example?
Well, one huge debate is realism versus anti-realism.
Okay, what does that mean?
Realists tend to think that science is genuinely discovering the truth about reality. Our best theories are, approximately true descriptions of how the world is, even the parts we can't see, like electrons or quarks.
So science is finding the real stuff.
That's the realist view, roughly. Anti-realists, on the other hand, are often more skeptical. They might say science gives us really useful models, great tools for predicting and controlling things.
But we shouldn't necessarily assume those models are literal pictures of reality.
Exactly, maybe they're just useful fictions or tools that work. The key thing for them is empirical adequacy. Does the theory match the observations? Whether it's really real is less important or maybe unknowable.
Wow, okay, that's a pretty fundamental difference in perspective. Is science truth-finding or just really effective tool-making?
It's a deep question, right?
Yeah.
And then you have other major ideas, like from Thomas Kuhn.
Paradigm shifts.
That's the one. Kuhn argued that science doesn't just smoothly accumulate facts. Instead, it goes through these periods of normal science within a shared framework, a paradigm, and then eventually crises hit, anomalies build up.
And the whole framework gets overthrown.
Leading to a scientific revolution, a paradigm shift, a whole new way of seeing that part of the world. Think Copernicus or Einstein. It's not just adding knowledge, it's restructuring it.
Like the world itself changes for the scientists involved.
In a sense, yes, their conceptual world certainly does. And then, taking things even further, you had Paul Feyerabend.
He sounds radical.
Oh, he was! He famously argued against the idea of a single scientific method. His view was sometimes called epistemological anarchism. Basically, anything goes.
Anything goes, like no rules.
Well, he argued that looking back at history, major breakthroughs often happened precisely because scientists broke the existing rules of method. So rigidly sticking to one method might actually stifle progress.
Okay, that's a challenge to everything we've just been talking about.
It is. These philosophical views really force us to think critically about what science is, its limitations, potential biases. It's not just a simple recipe.
No, clearly not. So, given all this, the methods, the philosophy, how do scientists actually build the theories that become so important? Walk us through that process.
Sure. Theory building is usually an iterative process. It often kicks off with some observation, something puzzling that needs explaining.
Okay, that's a weird moment.
Exactly. Then scientists propose a hypothesis, a tentative explanation, an educated guess.
Right.
And this hypothesis needs to be detestable. So the next step is rigorous testing through carefully designed experiments or maybe more focused observations.
Trying to prove it wrong, essentially.
Or at least see if it holds up. The results then feed back. If they support the hypothesis, it gains strength, maybe gets refined, becomes part of a broader theory. If the results contradict it,
Back to the drawing board.
pretty much. Revise the hypothesis or maybe discard it entirely and try a new idea. It's this continuous cycle. Observe, explain, test, refine.
And the logic we talked about, induction. Deduction fits in here.
Absolutely. You might use induction to spot a pattern and formulate the initial hypothesis. Then you use deduction to work out specific, testable consequences of that hypothesis. If my hypothesis is true, then this should happen under these conditions.
Makes sense.
And there are models for thinking about what makes a good scientific explanation. One classic one is the Deductive-Nomological Model, or DN model.
Okay, fancy name. What's the idea?
The basic idea is that you explain some particular event, some phenomenon, by showing that it follows logically deductively from a general scientific law. That's the nomological part, meaning law-like, plus some specific initial conditions.
So this happened because law X is true, and the situation was y.
Precisely.
Yeah.
Like, this apple fell at this acceleration because of the law of gravity, and because its mass was m and the Earth's mass is e, etc. It shows how the event was expected, given the laws and conditions.
Got it. That provides a kind of logical structure for explanation. Okay, this has been, well, incredibly clarifying. But it leaves me wondering, are there just some things science can't do? Limits to this whole approach?
That is a huge ongoing discussion. Many people think so.
Yes.
Given science's focus on the empirical, the measurable, the testable, maybe it's just not the right tool for certain kinds of questions.
Like questions about meaning or morality, subjective experience.
Exactly. Questions of value, purpose, consciousness. Maybe those lie outside the scope of what scientific methods can effectively tackle. That doesn't mean they aren't important questions, just maybe not scientific ones.
Interesting distinction. And within science itself, are there still big open frontiers?
Oh, absolutely. The quest for unification we mentioned, that's still very active.
Right.
Physicists dream of connecting quantum mechanics and general relativity, for example.
The theory of everything.
That's the ultimate ambition for some, yes. A single framework that explains all the fundamental forces in particles, whether that's actually achievable or even if such a single theory exists. Well, that's one of the biggest open questions in science.
So, despite centuries of incredible progress, there are still these vast fundamental mysteries.
Always. That's part of what keeps science exciting.
Well, this has been a fantastic deep dive, really illuminating. We've gone from the basic why of science, its roots, through telling it apart from pseudoscience, looked at the core methods,
Observation, experiment, induction, deduction.
then into the big philosophical debates about realism, paradigms, method itself,
Kuhn, Feyerabend. Challenging stuff.
how theories actually get built and tested, and finally, these huge open questions about limits and unification. Hopefully for you listening, this gives you a much richer sense of not just what science finds, but how it finds it, and all the thinking that goes on underneath.
Understanding the process, the debates, the framework, it helps you engage more critically and thoughtfully with science, I think.
Absolutely. A final thought to leave you with. Thinking about all this, the aims, the methods, the debates, the frontiers, what strikes you as the most exciting or maybe the most challenging area for science in the coming years? Where do you see the biggest questions or the biggest potential? Something to ponder. Thanks for joining us for this deep dive.